Welcome back to Chapter 20, Part 4. We're going to now just do a conclusion to our inference and hypothesis testing about a parameter. Well, first we're going to look back on how to construct a confidence interval about a parameter. It's always the statistic, the point estimate of that parameter, plus or minus a margin of error. The margin of error, remember, is a critical value times the standard error of our sampling distribution about that particular statistic. How do we calculate the test statistic in a test of significance for the hypothesis test? In other words, a hypothesis test or test of significance. Well, the test statistic is always that point estimate, the statistics, minus the value in the null hypothesis, which is the mean of our null hypothesis distribution, divided by the standard error of our null hypothesis distribution. Because remember, the null hypothesis distribution is a sampling distribution of whatever statistic we're looking at. If the population distribution is known to be normal, then all the sampling distributions of any size will be normally distributed. If we don't know anything about the population's distribution, or that the distribution is not normal, then if our sample size n is large enough, we can evoke the central limit theorem, which enables us to say that the sampling distribution is approximately normal. And if we're dealing with the mean, then that means that our sample size has to be 30 or more to say that the sampling distribution of the sample mean is approximately normal. Now, if n is less than 30, we must use data analysis on our sample. That is, we can use a probability plot and a box plot. We can determine if there are any major deviations from normality, that's the probability plot, with no outliers, and the box plot is great for showing outliers. If we do not have the probability and box plot, or do not have the data, we cannot construct the confidence intervals or do the hypothesis test with the techniques presented in Stat 250. Now, in order to evoke the central limit theorem for proportions, well, if we have a one-sample proportion problem, if the population proportion isn't close to or either 0 or 1, that is, n times p is greater than 10, or n times 1 minus p is greater than or equal to 10, then the central limit theorem can be evoked, and the sampling distribution of the sample proportion is approximately normally distributed. For the two sample proportions, n1 times p1 times 1 minus p1 has to be greater than or equal to 10, and n2 times p2 times 1 minus p2 has to be greater than or equal to 10. And of course, in order for the sampling distribution of this of the difference of proportions to be approximately normally distributed. But remember, we can have the +4 method that helps us if the sample sizes are a little bit smaller. So let's go back to Chapter 14 and 15, where we had one sample Z procedures. And what were the assumptions that had to be met? Well, of course, samples obtained by simple random sample, that's common for all of these. Normality has to be established, common for all. And this, sigma, was known. So the way we build our confidence interval is x bar plus or minus our critical value times sigma over the square root of n. Again, we see our statistic plus or minus the margin of error being this z alpha over 2 times sigma over the square root of n, the critical value times the standard error. And for our test of significance, we see all the null and alternatives hypotheses and how we calculate our test statistic, which is just the statistic minus the value in the null hypothesis, or the mean in our null hypothesis distribution, divided by the standard error in our null hypothesis distribution. That's the sigma divided by the square root of n. Now in Chapter 17, we had our one-sample T procedures. And again, samples were obtained by simple random sample, normality established, sigma is unknown. So we had to go to Table C, our student T distributions, where we had to know both our sample size and our confidence level in order to figure out what our critical value is. And so we create our confidence interval x bar plus or minus that critical value times the standard error of our sampling distribution. And our test statistic looks very similar to the test statistic for Chapter 14 and 15, except for you have the S instead of sigma. You have your sample standard deviation by the square root of n. That's the standard error of our sampling distribution. Now, the two-sample dependent case for T procedures, which was at the very end of Chapter 17, we were looking at, we got our samples that were obtained from simple random sample, the two samples that were dependent, created a distribution of the differences. And so we had to establish normality for those differences, and the sigma is unknown for the differences. So that put us into using, again, Table C. And so we found the mean of those differences, that's the statistic, plus or minus the margin of error, that would be our critical value, T alpha over 2 degrees of freedom, times the standard deviation of the differences divided by the square root of n, which is just our standard error. And our test statistic would look like x, the mean of our differences, divided by the standard deviation of the differences, divided by the square root of n. And remember, degrees of freedom are our sample size minus 1. For the two-sample independent t procedures, which was Chapter 18, both samples were obtained by simple random sample. Normality had to be established for each of the samples, and sigma is unknown again. So in order to, we did our approximation to the degrees of freedom, which gave us conservative confidence intervals. That means intervals that will be a little bit longer, and that it will be harder for us to reject the null hypothesis. Henceforth, it's conservative. And the way we do this is we take the smallest sample size and subtract it from 1, and that would give us the degrees of freedom. So you see here the calculation of our confidence interval. It's the statistic, and the statistic is the difference of the two sample means plus or minus our margin of error, where the margin of error is the critical value times the standard error. And there we have all the null and alternative hypotheses that you can see, the different ways that it can be written. And there's our test statistic. It's the statistic divided by, so it's the statistic x1 bar minus x2 bar divided by the standard error. Now, the reason why we don't subtract off the value in the null hypothesis, because in Stat 250 we said it's always going to be 0. Now we go to our proportions. Our one sample proportion, which was Chapter 19, our sample had to be obtained by a simple random sample and normality established. For the large sample confidence interval, again, our statistic is p hat plus or minus the margin of error. Remember, the margin of error is the critical value times the standard error. Now, if our sample size is small, and we have at least a 90% confidence interval, and that means our sample size n is at least 10. Then it counts as success and failure. We can do our +4 confidence interval. And that's our statistic now is p tilde, where we add these imaginary 4 successes and failures. So p tilde is going to be x plus 2 divided by n plus 4. You add 4 to the sample size, 2 successes and 2 failures. So we use p tilde instead of p hat. And so we have our new statistic, p tilde, plus or minus the margin of error, which is our critical value times the standard error. And as you can see, the standard error contains our p tildes. The test statistic for our hypothesis test is just p hat minus p naught. In other words, the statistic minus the mean in the null hypothesis distribution, which is just p naught, divided by the standard error. And for our two-sample proportion in Chapter 20, again, both samples had to be obtained by a simple random sample and normality established, as we talked about above. For the large sample confidence interval, it's our statistic. And our statistic for P1 minus P2 is P1 hat minus P2 hat, plus or minus the margin of error, where the margin of error, so Z alpha over 2 times the margin of error. Now, we can use the +4 confidence interval if our sample size is at least 5 in each group, with any counts of successes and failures. And again, you're going to add 4 between both samples, so you're going to add 2 to sample 1 and 2 to sample 2, and you're going to add 1 success and 1 failure to sample 1, and 1 success and 1 failure to sample 2. And then we have our hypothesis test with all the null and alternative hypothesis, and there's our test statistic. But remember, since we're assuming P1 equal P2, we use the pooled statistic for our standard error, and the pooled statistic is x1 plus x2 divided by n1 plus n2. So our test statistic, as you can see, is our statistic, P1 hat minus P2 hat, and since the value in our null hypothesis is always 0, we don't see that, divided by the standard error. Well, this concludes Chapter 20, and we will go to Chapter 21, which is a review chapter, and then the very last chapter, which is Chapter 22. So we're almost there. See you later.